Alright, our dear students, I welcome you once again to our revision ug.com. This is our lesson number 5. I congratulate you upon moving us with us from lesson number 1 to lesson number 5. So in this lesson, we are going to look at volumetric analysis. So this volumetric analysis, it is also a special subtopic under moral concept because it is also seen in paper 3 of chemistry. This is practicals, and it is always number 1, which is termed as titration. Always this titration, it is what we call acid base titration or base acid titration. So this one involves using two different substances with different volumes and with different concentrations. So but in this lesson this time we are not going to look at titration, but we are going to deal with the volumetric analysis in the essay form. So before we go any further, let us understand what is volumetric analysis. Volumetric analysis, it deals with the measuring or the measurements of volume of a solution, as I've said, by titration. And within this titration or within this measuring, during these measurements, when we are taking them, we are looking at molarity. We can get molarity from them, we can get concentration, we can get also the relative formula mass of the various substances that are being used, especially one is an alkali, another one is a base. Before we get started, a quick recap about this titration. We are having a base, then a base is normally put in the conical flask, and this volume is normally known. So the volume is normally known. Then we can pipette and we put it there. Then its concentration is not known. Then we can this is the burette. In the burette we are having a volume or a solution, and this solution, its concentration is known, then even the volume is also known. So using this known volume of the solution and the concentration, we can use it to crack the molarity, the relative formula mass of the second volume. Alright, there we go. Remember, keep with revision ug.com. Let us get started with our first example. The first example says 0.05 molar, and we remember from our lesson, from the previous lessons, we said that when the moment you see this M, this one stands for molarity. Now the moment you see this one stands for molarity. So this one is the sulfuric acid and its concentration is known. So was titrated against the solution of a base, and the base was MOH. Then 250 cubic centimeters of the alkali. This is not 250, this is just 25. This is just 25, not 250. This one is not there. Of the alkali required 24 cubic centimeters of the acid for complete neutralization. Calculate the molarity of the alkali. Right. So here, let us now get started with this one. We are having here 0. Let us now put this one into interpretation. This means that 100 cubic centimeters of a solution contain 0.05 moles, but moles of what? Moles of the sulfuric acid here. Right. Then how about, because now they are telling us that 24 cubic centimeters of the acid was required to neutralize the what? To neutralize the base, to be neutralized, sorry. Therefore, how about the 24 cubic centimeters there of a solution then produce the how many moles? That is 24 cubic centimeters all over 100 cubic centimeters times 0.05 moles there. So let us compute this one and we get to see what we are getting. This is 24 divide 24 by 1000. This is giving us that one, then times 0.05. So what are we having? We are getting 0.0012 moles there. Now after getting this, so we have obtained the moles. So these are the moles that reacted with the volume of the alkali, and the alkali was 25 cubic centimeters there, meaning that now we are going to compare. We are going to compare using what we call the mole ratio. So we are going to use what we call an equation, the stoichiometric equation here. Then at this level, we remember we need to get the molarity, but now these moles are for the acid. So let us write now the equation. We are having our base, which is MOH, reacting with, so reacting with the sulfuric what? The sulfuric acid. Then when they react with the sulfuric acid, what are we getting? We are getting, remember this is in valence 1, valence 1, meaning that now this is valence 2, so M2HSO4, and then this is going to be aqueous, then plus water, which is a liquid. So this is going to be aqueous, then this is going to be a liquid. So we balance it. To balance this one, we have to put a 2 here. Then when we put a 2, then there are 6 oxygens, and again 4 and 1. Then we put a 2 here. Then there are going to be 6 oxygens, 4 hydrogens, and there are going to be 2 and these 2, so 4 hydrogens, 1 sulfur, 1 sulfur. So the equation is now doing what? Balancing. After balancing the equation, we are now going to use what we call mole ratio. We are going to use what we call the mole ratio. Mole ratio here. We are going to use a mole ratio. I'm going to keep on rubbing. So mole ratio here, we are going to have this, whereby we are going to say we are comparing sulfuric acid and this alkali, whereby here we have 1 mole and here there are 2 moles. So we shall write and say 1 mole of a sulfuric acid reacted completely, or reacts completely with 2 moles of the alkali, or MH. Then how about how many moles these are? How about 0.002 moles, because that's the volume which reacted completely. Then we react, that will be 0.0012 out of 1 times 2, which is now going to give us 0.002 and 4 moles of MOH. Now these moles are these are the moles, and these are the moles of OH, of the alkali that reacted with the moles of these ones completely, meaning that these moles, if we compare them, they are the moles that are equivalent to the volume there, which means that now 25 cubic centimeters of the alkali, that is OMH, are contained 0.0024 moles there. Then how about now we want the molarity? How about 100 cubic centimeters of MOH? Then this is going to be 1000 out of 25 cubic centimeters times 0.0024 moles there. So let me first rub here. We get enough space. Yes, we get enough. We get enough space here. Okay, so when you look at this one, we are getting enough space. Then from here, what are we going to have? We are going now to compute. Let us compute this one. This is going to be 1000 divided by 25. We get that one. Then times 0.0024 times 0.0024. What are we getting? We get 0.096. So this is molarity, moles per liter. So that is our first our first question. Then our second question here, they are telling us that now after doing this one, find if the alkali contains 3.8 grams per liter of mH, what is the relative atomic mass? Relative atomic mass. So to get the relative atomic mass, we have to get the relative formula of MOH. Then this means that now in 1 liter, meaning that 3.8 grams represent 0.096 moles, because even these ones are in a liter, in moles in liters. Now this is now moles in terms of mass, meaning that now 0.096 moles here, they do what? Represent 3.8 grams. Then how about 1 mole? Remember we say that 1 mole of a substance is equivalent to its RFM. Therefore, how about 1 mole? This is going to be 1 out of 0.096 times 3.8, right? Then this one is going to give us, let us compute this. So this is going to be 1 divided by 0.9, oh sorry, divided by 0.096, right, is equal to that one, then times 3.8. Then what are we getting? We are getting 39.5, which is roughly 40 grams. Therefore, now if we are getting the relative atomic mass of this one, it means when we have M plus oxygen plus hydrogen, all of that one is 40 grams. Now M plus the 16 plus the 1 for hydrogen is giving us 40 or 39. Therefore, M plus 17 minus 17 is equal to 40. Actually, we can leave it as 39.5, 39.5, 39.5. Even this one we can leave it as 39.5, right? So minus 17, right? So our M is going to be equaling to that is minus 17. So the answer becomes 22.5, which is roughly giving us, it can also be 23. So that is the relative atomic mass for our substance M. My dear learner, are we still together? Let us now go and get our other example number 2. So when you are dealing with these numbers for volumetric analysis, you have to use critical thinking, you have to reason, you have to imagine, you have to use the 3 C's. Remember, keep up with the revision UG. For any misunderstanding, if you are misconception, if you are having a query, a question not well elaborate, please follow us using the links below. Now our example number 2 says 3.2 grams of impure sodium carbonate was dissolved in water to make 500 cubic centimeters of a solution. So they got impure carbonate, sodium carbonate, then they dissolved it in water, meaning that some impurities did not dissolve and the pure carbonate dissolved, right? Now they made a solution to 500 cubic centimeters, that is half a liter. Now they are telling us that 25 cubic centimeters of the solution required exactly 24 cubic centimeters of 0.1 molar. Now we are going to first put this one into interpretation. So this means that 1000 cubic centimeters of a solution contain 0.1 moles of hydrochloric acid. Then how about 24 cubic centimeters? Then 24 cubic centimeters of a solution will contain 24 out of 1000 times 0.1. Then what are we getting? Let us compute that one. We are having 24 divided by 1000. 1000 is equal to that one, then times 0.1. What are we getting? We are getting 0.002 and what? 4 moles. Now after getting this, we are going to get the mole ratio, but by writing the equation. Then the equation, we are writing sodium carbonate So sodium carbonate here reacting with hydrochloric acid, which is aqueous. Even this one is aqueous. Then we are going to get sodium chloride, which is aqueous, then plus carbon dioxide, which is a gas, then plus water, which is a liquid. Let me hope that you know how to complete and balance the equations, right? So sodium is there too. Now we have to put this balance, then we put this one also into balance. So hydrogen is there too, even hydrogen is here too, chloride 2, sodium 2, carbon 1, oxygen 2, 3, oxygen 3. The equation is now balancing. Therefore here we have 1 mole and here we have 2 moles. Therefore we are going to say by saying 2 moles of hydrochloric acid react completely with 1 mole of sodium carbonate at a standard. Now here we did not use 2 of them. How many were used? 0.2. How about 0.02 moles of HCl? They are now going to react with how many moles of sodium carbonate? If this one, that will be 0.0024 divided by 2, then times 1. Then what are we getting here? We are having 0.02, then divided by 2. What are we getting? We are getting just 0.001 and 2 moles. So this is the mole ratio, meaning that these moles, these are the moles of sodium carbonate that reacted with these moles, meaning that these moles that reacted are the moles that are involved in 25 cubic centimeters. Therefore we come here and conclude and say 25 cubic centimeters then of the sodium carbonate are contained as 0.0012 moles there, right? Then what are they asking? They want the molarity, then the number of moles in 1,000 cubic centimeters of a solution of a sodium carbonate. Then this is going to be 1,000, right, over 25, then by 0.0012. Then what are we having there? This is 1,000, 0.0012, then by 1,000, it's giving us that one. Then we divide it by 25. So what are we having? So it is 0.048 moles per liter. Remember, it was molarity. Then after getting the molarity, the question still says calculate the impurity, the percentage purity. Then when we look at the percentage purity, meaning that we need to know what mass was there which dissolved. Remember, the mass was 3.2, and again that mass contained the impure sodium carbonate. So meaning that the pure sodium carbonate dissolved, so and that one which dissolved is equivalent to 0.048. So we need to get the mass of that one. So and once we are getting the mass, what do you know? So far we know that when you are changing moles to mass, we are using the leading statement, which says 1 mole of a substance, 1 mole of a substance, leading statement, 1 mole of now a substance. What is the substance? We are dealing with the sodium carbonate here, is equivalent to its relative formula mass, right? Then the relative formula mass for sodium carbonate, it is sodium, 2 of them, you add 1 carbon atom, you add 3 oxygen atoms, then this is 23 by 2, then plus 12, then plus 3 by 16, then this is 46, then plus 12, then plus 48, which is totaling to 106 grams, which means that so this means that 1 mole, which means that this is 1 mole of sodium carbonate here is equivalent to 106 grams, which means that 106 grams of sodium carbonate, once you get them, they are giving us 1 mole. Then how about these moles that reacted completely with the HCl? Then this is going to be 1 mole. Oh sorry, oh gosh, it can remain there. Then this one can be reversed. Oh, let me not to waste time, let me rub this one. So 1 mole giving us this. Then how about this one? This is 0.048 moles here are going to give us 0.048 times 160 grams. So we are going to have then we multiply by 160. Then what are we having? So we are getting 5.088 grams here. Now so when you look at this one, these are the grams that are here, that are within here. But again, when you look at this one, this is for 1000 cubic centimeters, because we have said per liter, but this impurity was dissolved in 500 mils. So we are going to divide this one by 2 because it was dissolved in a half liter. So if we divide that one by 2, what are we getting? Then we are getting 2.544 grams. So out of the 3.2 grams, then the pure sodium carbonate was 2.555. So this is the pure. Then when you are getting the percentage purity now, this is going to be the purity, the pure sodium carbonate, that is 2.544 out of the total, that is 3, then times 100%. So this is going to be 244 divided by 3.2. This is giving us 0.79, then times 100%. Then it is 79.5%. So the percentage purity is 79.5%. Alright, that is volumetric analysis. Let us look at one other example here. This one other example says 8.58 grams of sodium carbonate X water of crystallization was dissolved in water and made it 1 liter. Then 20 cubic centimeters of this solution needed 12 cubic centimeters of 0.1 molar. And I told you the moment you see this one, we have to first put this one into interpretation just here. Then what does this mean? This means that 1000 cubic centimeters of a solution containing hydrochloric acid that produces 1.0 moles of HCl, right? Then how about the 12 cubic centimeters of a solution will now contain the 12 out of 1000 times 0.1 here. So what are we getting here? Then this is going to be 12 divided by this is 12 divided by 1000 gives us that one. Then multiply it by 0.1. So this is giving us a 0.0012 the moles there. So we are going in for the mole ratio, right? But before getting the mole ratio, we have to write the stoichiometric equation. This is going to be a sodium carbonate, because now we don't consider the water of crystallization, then plus the HCl, our HCl, hydrochloric acid, aqueous, then this is aqueous also. Then this is going to give us a sodium chloride, which is aqueous, then plus water here. Then sodiums, there are two, we balance here, then we also balance this, then we put also here, then the equation is balanced. Therefore mole ratio says then 2 moles of hydrochloric acid from the standard react with 1 mole of the sodium carbonate. Which sodium carbonate? Here there is 1 mole, and it's even this one is 1 mole. Alright, then how about 1 more? How about 0.0012 moles of hydrochloric acid will react with now 0.0012 divided by 2. Then this one is going to give us a 0 divide it by 2. This is going to give us a 0.0006 moles. Now this number of moles, that are moles of sodium carbonate decahydrate or X-hydrate, which reacted completely to cause the neutralization of the acid. Therefore, we come here and say, then what was the volume? The volume is here 20. Then the 20 cubic centimeters of the solution contained 0.0006 moles of the sodium of the sodium carbonate. Then we want the molarity. How about 1000 cubic centimeters of that solution will now contain 1000 cubic centimeters of the solution of 20 cubic centimeters by now the moles of this one from the mole ratio from this equation here. Then this is 0.0006 moles there. Then let us compute this one. It's that one, then times 1000 giving us that one, divide it by 20, so it is now 0.3 molarity, moles per liter there. Then the question says find the value of X. Now to find the value of X, what does it mean? To find the value of X, it means we need to get the relative formula mass of all of this. Then when we get of all of the relative formula mass of all of this, we need to get now for that X. But before doing that, we need to know to get this, meaning that this is the concentration in moles, but this is the mass. Are we getting? And this mass was dissolved in a liter, meaning that now this is 8.58 grams per liter, which is now equivalent to 0.3 moles per liter. Has it made sense? It is. 8.58 grams of sodium carbonate was dissolved in water to make 1 liter, meaning that now that's the concentration in grams. Then what we have done is the concentration in moles, meaning that 0.3 moles, the equivalent to 8.5 grams in terms of mass. Understood? Right. Now this is what I mean. So the 0.3 moles are equivalent to 8.58 grams, right? Then how about 1 mole? Because 1 mole is the one which is giving us the relative formula mass for the full compound. Then this will be 1 out of 0.3 times 8.58 grams. So this is a point, don't forget. So let us compute this one. This is 1 divided by 0.3 giving us that one, then times 8.58. what is the answer? Sorry, this is this is 1000, then divide by this one gives us that one, then times 0.123, this one gives us a 0.03. then this is this one, here it is 0. I think the point is here, 0.3. then we compute this one, which is going to be 1 divided by 0.003 gives us that one, then times 8.58 giving us a 286 grams, which means that now the relative formula mass for our compound there, it is 800 it is 286 grams. Let me first cleanse here. Yes, clean this one. Yes, now we have space clearly. Okay, now this means that the RFM of sodium carbonate here is equivalent to 286 grams. So meaning that when you get a sodium atom, 2 of them, plus carbon atom 1, plus 3 oxygen atoms, plus X into water atoms, we get 286 grams. Now this is going to be 23 times 2, then this is going to be 12, then this is going to be 3 times 16, this is going to be X into 18, because 2 plus 16, that is 18, giving us 286 grams. Now this is 46 plus 12 plus 48 plus X into 18 into this 18 gives us 286 grams. Now this is 106 minus 160 plus 18x gives us 286 minus 106. Therefore 18x gives us let us subtract that, then take off 106 gives us 180, so we divide by 18, so this x here is equal to 18 here, it is a 10. Therefore the value of x is equal to 10. Then our formula will be a sodium carbonate this is 10H2O. Alright, so let me hope that you've understood. Where you are stuck, try to contact us and try to replay the video. You'll understand it the more time you play it. Let us get our last example. Alright, so this last example here, they are telling us that 25 cubic centimeters of a solution containing 5.3 grams per liter of a metal carbonate of formula M this, then neutralized by this of this hydrochloric, this is not hydroxide, this is hydrochloric acid. Calculate the molarity of the carbonate and so on. So let us start with the molarity. So as we are getting the molarity, I told you when you see this, we first put this one into interpretation. What does this mean? This means that 1000 cubic centimeters of a solution contain 0.1 moles of the hydrochloric acid. Then which volume was needed to neutralize that one? So 25 cubic centimeters of a solution, then neutralized by 25 cubic centimeters of the acid, meaning that 25 cubic centimeters of that acid of a solution will contain now 25 cubic centimeters all over the 1000 cubic centimeters, then by 0.1. So we get the moles of the acid there, which is going to be 25 by 1000, giving us that one, then times 0.1, this is 0, this is 0.0025 25 what moles. Then after this we are going in for the mole ratio, but before doing that one we have to write the stoichiometric equation, whereby we are having metal carbonate M, M2 carbonate, then plus the hydrochloric acid, which is aqueous, even this one is aqueous. Then what are we getting? Then meaning that this metal, it is in valence 1. Therefore we are going to get M chloride, which is aqueous, then plus water there, which is a liquid, then plus carbon dioxide, which is a gas. Therefore here we are balancing, so we put a 2 here. When you put a 2, we balance also here. So the equation, I think it is balancing 1 carbon, 6, these are 3, then 3, then 2 hydrogens, 2 M's, 2 M's, right? Now we go for mole ratio. So 2 moles of hydrochloric acid here react completely with from the equation, completely with 1 mole 1 mole of metal carbonate here. Then how about these moles here? 0.0025 moles of hydrochloric acid will react completely with now 0.0025 all over a 2. So it's going to have the moles. So this is going to produce, divide this one by 2, so it is producing 0.00125 and moles there. So, and these moles now, they are the moles of our metal carbonate, but a question requires us to get the molarity. So the moles of our metal carbonate and these moles of the metal carbonate, they are in the 25 cubic centimeters. So the 25 cubic centimeters of a solution containing a metal carbonate will now produce 0.0012 moles. Then how about the molarity? That is 1,000 cubic centimeters of a solution will now contain 1,000 cubic centimeters all over 25 cubic centimeters times 0.00125 there. So let us compute that one. So this one times 1,000 gives us that one. Then we divide it by 25. We get this is 0.05 moles per liter. So that this is our molarity. Then after that, they want us to get the formula mass of the metal. The formula mass of the metal. Remember, 5.3 grams per liter. So it's equivalent to this one. Therefore, 0.0 now Roman 2 here, 0.05 moles now contain equivalent to 5.3 grams. Then how about 1 mole here will now contain, or will give us 1 out of 0.05 times 5.3 there. Then this is going to give us 1 divided by 0.05, right, gives us this, then times 5.3. This is so it is 160 grams. So this is the relative formula mass for metal M. Then Roman 3, they are telling us that get the relative atomic mass. So after getting the relative formula mass for the whole compound, then we can get that one for the M only. Let me rub this one, we get space. So we get space. Please don't forget to subscribe, like and share with your friends. So now let us do this, the last one, Roman 3 here, relative atomic mass. So relative atomic mass of M there. So we are going to have M. So M, there are 2 of them, 2, then plus 1 carbon, then plus 3 oxygens. They are giving us 160 grams there. Okay, then 2M plus 12, then plus 3 times 16 gives us 106. Therefore, this is 2m plus 12 plus 48 gives us 106. So 2m plus, this is a 10 we put here, we bring down, this is 5 6, so 60 minus 60 gives us 106 minus 60. Therefore 2m is equal to 106 minus 60 minus 60 gives us 46. Divide by 2, so m is equal to 23. Therefore the relative atomic mass of m is 40, not 43, it is 23. So please, if you've not understood, please try to contact us using the links in the description table below, and please, I urge you to play the video over and over. So in this lesson 5, we are not having the task, but the task you are going to get it as you connect, or you link, you tap in the link in the description table or box below. So keep up with Revision Uganda.ug. We meet in the next lesson.